Okay, let's go for a little bit, and then we'll talk about other stuff for a bit. Okay? Okay, so today we are going to talk about computing the GCD. Okay, so Euclid's GCD algorithm. How do you compute inverses mod n? Then we'll talk about functions, bijections, and RSA. Okay? So let's start. Okay, so first, everybody know what we mean by GCD? Yeah, it's the greatest common divisor. Okay, so what's the most direct way of computing the GCD? Yes. I'm sorry? That's a really, yeah, that's the most direct way. So you just try numbers, right? You start with 2, 3, 4, 5, keep trying every one in turn until you find one, and then keep checking which is a common divisor. By the time you get to the smaller of the two, you've figured out which is the greatest common, right? Because the greatest common divisor can't be bigger than the smaller of the two numbers. So that's definitely sort of the most elementary approach to computing the GCD. Okay, so how about a still elementary but slightly less so? Yes. Okay, so good. Compute the prime factorization. So what you might do is write 60 as, what are the prime factors of 60? So it's 2 times 30, 2 times 2 times 15. So it's 2 squared times 15 is 3 times 5, right? Do the same for 42. What's 42? It's 2 times 21. 2 times 3 times 7. And now what you do is find the biggest prime powers that are common to the two. Right? So in this case, the prime powers that are common, well, 2 just goes once here and twice here, so the common factor is 2. 3 goes in both, and then 5 and 7 they're not common factors. So the GCD is going to be 2 times 3, which is 6. Okay. Yes? So that's computing the GCD. Now, what's wrong with that? Well, on the face of it, nothing, except for the fact that factoring is a hard problem. Okay? Factoring is really hard. It takes exponential time. Okay, so what does it mean it takes exponential time? The way we measure the time that algorithms take is in terms of what kind of function is it in terms of the length of the input. So if your input is n, okay, n is not the length of the input, right? So if n was whatever 42, the input length is just how many keystrokes it takes you to input n into the computer. So for this, you would say the number of keystrokes you need is 2, so the length is 2. Or if you were writing out 42 in binary, then it would be a little longer. You might need 5 or 6 keystrokes. So that would be the length of the number. So if your input is n, then the length of the input is the number of keystrokes, which is about log n. Does everyone understand this? Okay. All right. So let's do this slowly. Right? Okay. So suppose that the length of your number is little n. Now, how do you write your numbers? Shall we pretend you all write your numbers in binary? Okay? Let's pretend. Okay. So if the number of keystrokes is little n, so you have little n bits, how big is the number itself? Right? So you have little n bits. Okay. So if you have a number in binary that you can write out using 10 bits, how big is the number? It's about 2 to the 10, right? Yes? 2 to the n is about, 2 to the 10 is about how big? Is it about 1,000? 1,024. Okay, so it's about 1,000. So even though n, little n is 10, capital N is going to be about 1,000, right? If you have little n is 20, what's 2 to the 20? Two to the 20 is 2 to the 10 times 2 to the 10. So it's 1,000 times 1,000, which is about 1,000,000, right? So little n is 20, capital N is 1,000,000, right? Little n is 30, capital N is 1,000 times 1,000,000 is 1,000,000,000, right? Okay. Little n is 40, you get up to 1,000,000,000,000. Okay, it's going pretty fast, right? Okay. Already by the time little n is a few hundred, capital N becomes sort of impossibly large, right? It becomes larger than the number of particles in the universe. That's exponential growth for you, right? So capital N and little n are very different. Capital N bits corresponds, then n, the number itself is about 2 to the little n. Right? So you turn this around and you say little n is about log of capital N to the base 2. Yes? Is that okay? Okay. So now, here's what we are interested in. We want to, we are interested in using numbers which are, say, a few hundred bits long. So little n is going to be a few hundred bits. What's capital N? Capital N is huge. Yes? Capital N is very large. But little n is a, it's a few hundred, it's a few hundred decimal digits or a few hundred bits. And we want to know how easy is it to factor this number as a function of little n, right? So when you're using these numbers for cryptography, you might have a number which is about maybe a few hundred decimal digits long, so which is a few thousand bits long, right? 1,000, 2,000, 10,000 bits, something like that. So we want to know how hard is it to factor such a number as a function of little n. And the answer is the best algorithms that we have take time which is exponential in, oops, sorry, this was incorrect. It's exponential in big O of square root of little n. Okay? So it's exponential. It's, you can save a little bit. It's not exponential in little n, but it's at least exponential in the square root of little n. So a little bit better than we could, it could have been, but still exponential time. Okay? Now, sorry, we've been assuming that everybody in this class already saw big O notation. So let me just try to clarify what we, why we use big O notation and exactly what it is, in case you haven't, you haven't really seen a precise definition. So, you see, the reason we use big O notation is because when we are talking about algorithms, precisely how you implement them, your algorithm, precisely which program you write, tells you how many steps the algorithm takes or how long the algorithm takes, your program takes to run on an input of length little n. But often we are not interested in the exact details of your running time. What we care about is sort of these large picture, these large differences between, is your algorithm exponential time? Is it polynomial time? Does it run in roughly 2 to the n time? Does it run in roughly n squared steps? Does it run in roughly n steps? Right? So that's going to make a big difference in what your algorithm looks like or how well it's going to do. And then once you have these big parameters right, then of course you have to tune your algorithm and make sure that roughly n squared might mean 2 times n squared, or it might mean 1,000,000 times n squared, right? These are very, very different, okay? And of course you have to focus on these differences too. But as a rough cut, we'll hide these constants, okay? And that's what we do in big O notation. So here's what big O notation really means formally. So we have two functions, f of x and g of x, right? So think of these as the running time of two different programs, right? On an input of length, x, the first program runs in time f of x. The second program runs in time g of x. And we want to compare how well do they do against each other. So what we say is that f of x is big O of g of x if f doesn't grow much faster than g. So if there's some, so here's what we mean. So here's x, here's f of x or g of x. Okay, so let me draw them in different colors, g and g of x. Okay, and so possibly this is what your function, this is what your function g of x looks like. Oops, maybe we want it. Okay, so maybe this is what it looks like. It sort of grows like this. And f of x, well, f of x might grow like that. Sorry, let me in fact illustrate the point that I wanted to illustrate. So maybe g of x grows like that, and f of x perhaps it sort of grows. It starts off being bigger than g, and then it stays bigger, but it's sort of, you can see it's growing at a slower rate. It's growing, but at a slower rate. So now what we're going to say is, well, surely is f of x equal to big O of g of x? Okay. Well, so f of x here, f of 0 is certainly not smaller than any constant times g of 0, because at 0, g of 0 is exactly 0, right? So nothing you can multiply g by is going to make it larger than f. So this condition doesn't hold. But notice that it says it only has to hold after a certain point. So we can pick x naught as we want. So we could pick this to be x naught, and we can say after this point, if you multiply g by some value, then it dominates f, right? So, okay, so let's pick this to be x naught, and now we'll multiply g by some constant so that we bring it above this. So this is some c times g of x, and now what we want to say is c times g of x dominates f of x everywhere, as long as you're to the right of x naught. That's what it means to say f of x is big O of g of x. It doesn't grow any faster than g of x as long as you don't pay attention to constant factors. Okay? So, for example, if so, let's say it was a function of let's say it was a running time. So we had f of n. So let's say f of n was n. Was 3n. G of n was equal to n. Is f of n equal to big O of g of n? Yes, right? Because even though f is larger than g, if you ignore a constant factor, if you multiply g by 3 or 4, anything larger than 3, then f is less than or equal to g. Yes? If f of n is 1000 n, g of n equal to n squared, is f of n equal to big O of g of n? Yeah, it is, right? Because n squared grows, as n gets large, it grows very fast, right? Whereas, g of n grows very fast, but f of n, it starts off, there's this constant factor of 1000, but then it just doesn't grow that fast. So another way of saying that f is big O of g is just saying, well, the limit of f of x over g of x is less than infinity. The lim sup as x tends to infinity. Right? That's what it's saying. That it tends to some constant so it doesn't tend to infinity, the f over g, as x tends to infinity. Yeah? Okay. Everyone clear about this? Yes. Yeah, so just say the limit, so all we want to do is make sure that we take the, so the limit may not exist, and so you take the upper bound on the limit, right? Yes?
If f(x) grows approximately fast as g of x, so that f(x) over g of x limit as it goes to infinity is constant,
yeah.
Is that a member of code?
Yeah, yes. Yeah. Now, some of you, this brings up a good point. What you might see in some places is, instead of writing f of x is big O of g of x, people write f of x belongs to big O of g of x. And actually, this is the correct notation, except nobody uses it. Okay? So if you think about what big O means, big O is a class of functions which grow not, which don't grow faster than g of x, and we are saying f of x is one of those, right? So that's why the belongs to, but so if you care about these things, think about it, and if you're really a stickler for notation, do it, but it's a losing battle to convince other people to do it. So, yes, yeah. I was just saying, what does it mean that f of x is big O of g of x? Another way of understanding that definition, if you want to see it in different terms, is just think of the limit of f of x over g of x, and that doesn't diverge, that doesn't blow up on you. So that's what it means. Yes?
On the previous slide, you said that the thing blows up exponentially in little n.
Yeah.
But since little n is like log of big N,
yeah.
then isn't it less than linear in big N?
Oh yes, it's much less than linear in big N. Yes.
So isn't that all right?
Well, it depends upon what you're trying to do. If the number you're trying to factor is something that you can comprehend, yes, then it's great. But the numbers we want to factor are numbers which are 1,000 digits long, right? So once you say it's 1,000 digits long, then how big is n?
Too big.
It's 10 to the 1,000. 10 to the 1,000, you don't want to mess with 10 to the 1,000. That's huge, right? Yeah. Yes.
But for that limit, should it be g over x or f of x?
Should it be this limit? Should it be g over f? So we want to say f is growing slower than g, right? So we want to say f over g is bounded, right? So if it was g over f, then g over f can blow up on you. It can get arbitrarily large.
So if that limit is true, then f of x is big O of g of x?
That's right. So we are saying if that limit is bounded, if it's less than, if it's less than some finite number, right? So the way I wrote that is if it's less than infinity.
But then if you plug in the bottom line f of n equals 1000n and g of n equals n squared.
Yeah. So let's do that. So you write down 1000 n divided by n squared. The limit as n tends to infinity, so you can cancel the n's. So it's 1000 divided by n. What's the limit as n tends to infinity? 0. So it's less than infinity, so that's good. We are good. So f is little o of g, is big O of g of x. Yeah? Okay. Okay, so what does this bring us back to? It brings us back to this question we started with. How do you compute GCDs? Right? So we saw the easy way to do it is you just factor the two numbers that you're trying to compute GCD of and then pick the common factors, common prime factors, right? But that's going to take too long. So we want a method of computing GCDs without factoring. Now, luckily, there was an ancient Greek man who thought about the same problem. And, this was before computers, but why he wanted to compute GCDs of large numbers, we don't exactly know, but we are lucky that he did. And so this is one of the oldest algorithms we know of. Okay, so how do you compute GCDs? How many of you have seen Euclid's algorithm? Okay, good. So shall we do it? Let's try to run through it. So this is Euclid's algorithm. So what you do is take the bigger number, divide it by the smaller number. So it's 1 times 42 plus 18. Then you divide this number by that number. So you take 42 and write that as divided by 18. So it's 2 times 18. Maybe I should write that like this, so it's not plus 6. Then you write 18 equal to 3 times 6 plus 0. And when we get down to 0, we say this last number, that's the GCD. Right? So we say this is equal to 6. Okay? How many of you have never seen this before? Oh, good. You're lucky. This must be a bit of a surprise then. Okay, is the procedure clear? Okay, so here's the algorithm. Here's the code for it. So we are trying to compute the GCD of two numbers, x and y. We'll assume x and y are both non-negative. And we'll assume that x is positive, strictly positive, right? It's greater than 0. Okay. So it's an easy recursive algorithm. All it says is if y is 0, then you're done. You can return x. That's the GCD. Otherwise, you replace x by y and y by x mod y. So it's a remainder when you divide x by y. Right? Does everybody see that this is exactly what we did in that example? It's just, we're just implementing what we just did in the example, but implementing it as recursive code, right? Yeah? Is it clear? Yeah. Okay, so now we want to do two things here. We want to show that this actually works. So we want to prove that this algorithm works, right? That it actually computes the GCD. And the second thing that we want to do is we want to bound the running time. We want to show that it doesn't take exponential time. That it actually takes a number of steps, which is bounded by a polynomial in the length of x and y. No? No, that's not nice. Okay. So, all right, let's, so we want to prove that it works. Okay. So how should we prove that this algorithm is correct? Oh, good. Yeah, let's do an induction. Okay, but what are we going to do an induction on? What should we do an induction on here? Yes? Number of steps. Number of steps. Oh, but induction, no, but we want to say, okay, so here's the sort of, here's what we want to say, that this algorithm that we've written correctly computes the GCD of x and y, right? So what should we do an induction on? I'm sorry? On y. Okay, so we could do it on y. Tell me how you came to that conclusion, that you should do it on y. Oh, good. That's a dead giveaway, right? So the base case is y equal to 0. That's very good. And then? Good, good. Okay, so does everyone follow the reasoning? I mean, it's a bit of a leap to see what you should do an induction on. Right? When you have two arguments like this, maybe you want to do a double induction. Maybe you wanted to do an induction on x plus y. In this case, it's all a little bit simpler. You can just do an induction on y. You can ignore x. Right? Because when y equal to 0, right, we are just saying the GCD of 0 and anything x, x is greater than 0. The GCD of x and 0 is just x. Right? Because anything divides 0. Yeah? Okay, so what we are going to do, oops, that's the, okay, so we do a proof by induction on y. Right, so the base case, y equal to 0, it's fine, right? Because the GCD of x and 0 is just x. And that's what our algorithm is saying. So what should our induction hypothesis say? So it should say it works all the way up to y, right? So algorithm correctly computes GCD for y less than or equal to z. And now induction step. So I don't know, what did we call the algorithm? Was it GCD? Let me assume it was GCD of x z plus 1. Right? And we want to understand how that works. Yes? So what does it do? It says this is equal to GCD of z plus 1 y mod z plus 1. Sorry, x mod z plus 1. Okay. Right? So now this is less than or equal to z. Right? So what in the induction, so what our algorithm does is when we invoke it on this function, right? So sorry, let me just check what the, yeah, it was GCD. So when we invoke it on these inputs, it actually invokes itself recursively on this input, right? But on this input, x mod z plus 1 is less than or equal to z, so we can assume by the induction hypothesis that this recursive call to GCD gives you the correct answer, right? But it is the correct answer to the input z plus 1 x mod z plus 1. So we want to now say that the correct answer to that recursive call is also the correct answer to the original GCD we were trying to compute. Yeah. Okay, so let me say this, let me write this out more explicitly. Okay, so when we invoke GCD of x z plus 1, this makes a recursive call to that. Yes. Now, because the recursive call to is to this program with second argument less than or equal to z, we can assume by the inductive hypothesis that this program is actually correctly computing the GCD of z plus 1 and x mod z plus 1. And so all we need to do is we need to now prove that this answer, whatever it was, is actually the correct answer to the problem that we started with, which is computing the GCD of x and z plus 1. Okay, so what remains to show, so what we need to show is that the GCD of any two numbers x z plus 1 is equal to GCD of z plus 1 x mod z plus 1, right? Or more generally, that the GCD of AB equal to GCD of B A mod B, right? Where we are assuming that A is greater than or equal to B is greater than or equal to 0, and A is greater than 0. Right? These were our conditions. I'm sorry?
What were the conditions that you just wrote on?
Oh, sorry. So the conditions were what we had before. So our conditions were A is bigger than or equal to B is bigger than or equal to 0. And we also want to make sure that A is strictly bigger than 0. Yeah? So can anyone see why GCD of A and B is the same as GCD of B and A mod B? Actually, what's A mod B? It's of the form A minus KB, right? In fact, we can say GCD of A and B is the same as GCD of A and of B and A minus K times B, right? Because if D divides A and B, then D certainly divides B. It also divides any linear combination of A and B. If D divides B and A minus KB, then it divides B, and it also divides A because A is a linear combination of B and A minus KB. Right? So what are we using as a lemma? Remember we had this lemma that if D divides A and D divides B, then D divides KA plus LB for any K and L. Remember this lemma we had once upon a time? We've written it out many times. So, okay, that's all we're using. Okay? Okay. Let's do one last thing. Let's work through the running time bound and then take a break. Actually, let's take a break. Okay. So, let's see. I hope you know that there's a midterm coming up next week, next Thursday, in class, and it's going to cover material through RSA, right? So I'll get to some of RSA today, most of it on Thursday. So that's how much we are going to cover, and you know, this homework that you have this week covers through RSA, and so that's what we're covering. There's going to be, I guess, you know, there's going to be a review session. If you haven't already, there's a post about it on Piazza, asking you to look at, you know, sort of examples of past questions. You know, just think about which ones you would like to see them cover in the review session. Okay. Also, we'll provide you with some sort of um, some more information about the midterm, so you know sort of what are the the important topics. What are the skills that we are assuming you have? What are the topics that you should understand going into the midterm, and what kind of skills you should have going into the midterm? Okay, so think of it as a helpful study guide, which sort of tells you at this point, we've covered all kinds of material, but what is it moving forward that you should really know for the midterm as well as for what comes later in class, as we go beyond the midterm. Okay? Yes?
How did you say that those two are equal at the end?
How did I say which two are equal?
The GCD of A and B is equal to the GCD of B, A minus
Okay, so I said so here sorry, yeah, that's a good point. So let's see. We said if D is if D is a common factor of A and B, then it's a common factor of B and A minus KB. And we said if D is a common factor of A and B and A minus KB, then it also must be a common factor of A and B. So the common factors of A and B are exactly the same as the common factors of A and B and A minus KB. So their GCDs must be the same. The greatest ones must also be the same. Okay? And so how did we say that any common factor of these two must be a common factor of these two? Well, if D is a common factor of A and B, D is certainly a factor of B. It's also a factor of A minus KB by this, and similarly going backwards. Yeah? Yes?
For next week, are we learning anything new or getting any homework, or is it all focused on the lab?
No, there is going to be a homework, and we are going to be learning, we are going to be going over new stuff. The new stuff is going to be actually working with integers mod at prime. So we'll be looking at modular arithmetic, where you're working mod m, but m is now going to be a prime. Okay, so it's going to be going into new properties, but in some sense, it's only going to reinforce what you've been, it'll make what we've done in modular arithmetic seem a little bit easier because you move on further. Yeah? Yes? It won't be on the midterm. Yeah? Okay. Okay, so let's move on. Let's try to, so we now know that this algorithm is correct. It computes the greatest common divisor. Now we want to know, is it fast? Okay? And so to know that it's fast, the way we show that an algorithm is fast is we show that it's making a lot of progress. Okay? So we have to have some measure of progress. Okay? So what should our measure of progress be? Remember what we are doing in computing GCDs. We are saying if you're computing the GCD of x and y, then in the next step, you replace this by GCD of y and x mod y. Okay. So why is this a good thing? Why is this, why are we galloping along towards the goal? Right, so we want to keep going until we get down to 0. But why is this making a lot of progress? Yes? But y got replaced by x mod y, right? So how fast could that be?
It's going down by at so x mod y
Yeah.
goes down from x by x to y. So these x minus y.
So let's see. So suppose you had, suppose you were looking at something like this. Suppose y was, whatever it was, well, what would you like? 18? 18? suppose x was 35. Yes? So the next time around you'd go to 18, and now what's 35 mod 18? 17. So y didn't go down by very much, right? But somehow you had a good idea there, but it's a little subtle. You have to do something to make it all work out. So in what sense is this? So something has changed a lot, but what's changing here? Well, x dropped pretty fast here, didn't it? Yeah. But now look at a different example then. So suppose we had started with 35 and 34. Right? So the next time around we are going to go to 34 and 1, right? So x didn't drop very fast either. But this time y dropped very fast. Well, maybe it's the sum of the two, right? So it's a bit tricky, right, to figure out what's dropping fast. So, and I think the sum might, well, actually, will the sum work? Maybe. Okay, so here's something that works. Okay, so this is why, when you're analyzing these things, it can be a little bit tricky. But now if you go one more step forward, then you're computing GCD of x mod y and then something, right? So now what we could say is in 2 steps, x went from x to x mod y. And we can claim that's good. X mod y cannot be, going from x to x mod y, that really is a big change. Okay, so how do you see that? Well, see, there are 2 cases. So we are going to claim that x mod y is at most x over 2. And the reason this is true is there are 2 cases. Actually, there are 2 cases. It's by figure. Here's 0. Here's x. Now, where should we put y? So here's x over 2. Okay. Now, if y is down here, then what's x mod y? Well, if y is down here, x mod y is certainly going to be between 0 and y minus 1, so it's smaller than x over 2. Right? If y is smaller than x over 2, certainly x mod y is something that's smaller than y, so it's less than or equal to x over 2. How about if y is here? What's x mod y? Yeah, because now x mod y is this length, right? It's x minus y, so it's smaller than x over 2. So in either case, x mod y is smaller than or equal to x over 2. Okay. So how many iterations do we need before we terminate the procedure? Every 2 times through the loop, every 2 recursive calls, x is going to halve. Right? So how many times before we get down to a small enough number? Well, it's log base 2 of x. Right? That's how long it takes. Right? Now, that's how many iterations it takes. Each such iteration involves computing x mod y. How long does this take? Well, that's a division. So it's this many divisions. Okay, but how long does a division take? Well, if you really implement it properly, it takes quadratic time. So it's going to take order. So if you let the length of the numbers be little n, then it takes order n cubed steps. Because each division takes order n squared steps in the worst case. Right? Okay, so all this is stuff you'll learn about more in CS 170. This is just a bit of a preview of it for you. Okay. Is everyone okay with this? Okay, so now let's go back and compute GCD of 60 and 42 again, now that we know the algorithm. So what did we do? We said 60 was equal to 1 times 42 plus 18. 42 was 2 times 18 plus 6. 18 was 3 times 6. Okay? And so then we said the GCD is equal to 6. But now, those of you who've already seen how to compute GCDs, probably in high school or in grade school, wherever it was, there was probably another part of this procedure that you may or may not have done, which is called extended GCD or extended Euclid, right? Where you went back and substituted. So what did you do? You said 42 was 2 times 18 plus 6. And then you substitute 18 from here. And you say, so you say, well, first of all, from here you get 6 equal to 42 minus 2 times 18. And now you substitute for 18 from here, and you say 6 equal to 42 minus 2 times 18, minus 2 times 18 was 60 minus 1 times 42. And so you get 6 equal to minus 2 times 60 plus 42 times 1 plus 2, which is 3 times 42. Okay? So in general, if you computed GCD of x and y equal to d, then if you do this back substitution procedure, what this back substitution procedure will give you is not only the GCD, which is d, but it will also give you two numbers, a and b, such that a times x plus b times y equal to d. So in our case, d is equal to 6, a was equal to minus 2, and b was equal to 3. Okay? So for those of you who saw it in high school or in grade school, this would have been a mysterious part of Euclid's algorithm. Why would you ever care to do something like this? So did anybody actually see this in school? Yeah? And did you ever ask why you were doing this? I'm sorry?
It was so that.
Oh my God. Wow, who did you have as a math teacher? Okay, I see. All right. That's great. Okay, so we have another use for it today. Okay, so, oops. So first of all, here's how the extended Euclid algorithm works. Right? So now your recursive call to extended Euclid gives you back D, A, and B, right? And then what you do is you return, the same D, and then A prime and B prime, where A prime is just B, and B prime is this thing. Okay, so how do you make sense of this? Let me just show you. So when you called extended Euclid on y and x mod y, so what you got back was a times y plus b times x mod y. X mod y, let's assume it's x minus ky. is equal to d. And now you want to figure out what's a prime and b prime. So what you want is a prime x plus b prime y equal to d. So you want to figure out what a prime and b prime are. So you just rearrange, right? So you get b times x plus y times a minus kb equal to d. And that's exactly what this says, right? So d is the same. A prime is b. And what's b prime? B prime is a minus kb. Right? So this is equal to k. That's b. Okay? Make sense? Yes? Okay, so remember, we have a recursive procedure. What's the recursive procedure doing? We called it on y and x mod y. What did it return? It returned the GCD, and it also returned a and b, such that a times y plus b times x mod y equal to d. So all I've done is I've taken that, rearranged, so I get a prime times x plus b prime times y equal to d. And then I read off a prime, b prime, and they are exactly what we got here. So that's what the procedure is doing. Okay. What has this got to do with anything? Okay, remember this theorem from last time? We said when we are trying to compute the inverse of x mod m, we are now back to working mod m, right? Remember from last time we were working modulo m? We said we could add numbers, we could multiply numbers, we could subtract, and then we could divide if we were dividing by something which was, well, it wasn't 0, but moreover, we couldn't divide when there was a common factor, right? So if we said we could divide by a, well, we could divide by x, provided x was relatively prime to our modulus. Okay? Remember? Okay. So the question is, how do we find the inverse? How do we find, okay, so we said if x times y is congruent to, so if GCD of x and m is 1, then there's always a unique y such that x times y is congruent to 1 mod m. And we say that y equal to x inverse mod m. This is our multiplicative inverse. It's like 1 over x mod m. Okay, so how do we find y? Okay, so the question was, how do you find this multiplicative inverse? How do you find x inverse? So here's the answer. Compute this extended GCD on x and m. Right? So run Euclid's algorithm on x and m. So when you do this extended, did we call it extended GCD of x and m? What will you get? You'll get a and b such that a times x plus b times m equal to 1. Okay? So now what do we know about a times x mod m? Right? Everyone see that? Yes? So what's x inverse mod m? Right, so Euclid's algorithm will just give us back the multiplicative inverse. So it tells us how to divide mod m. Okay? Euclid didn't know he was doing this, but that's what he did. Do you want a minute? A break? A minute? Sigma. Okay, let me ask you a quick question. So, when you study, or when you've been, when you've been told about good study habits, is it to focus for a long period of time or for a short period of time? When people told you how to study well, are you supposed to be able to study for long periods of time or short periods of time? What's your parents, teachers, what have they told you to do? I'm sorry?
Study for like 1 hour with like ninja-like focus, and you break for like 60 minutes, 30 minutes, and then you study again.
Okay, so 1 hour with ninja-like focus and then 15-minute, 20-minute breaks. Yes?
And then another thing that I've heard is that your attention span is greatest at the very beginning of when you study, and that's the very end of when you study. So someone was telling me like half-hour chunks with like little 5 to 10 minute breaks in between.
Oh, I see. Half-hour chunks, okay. Okay, that's good, half-hour chunks. Anything else? Yeah. Let's finish. Is this related to what we are discussing, or no? Okay, so then let's. Yeah. Sorry. Any other responses? Yes. Yeah. Yeah. Okay, so then you have these 3-hour exams, so you have got to be able to focus for 3 hours or at least 1.5 hours. Right? So those sort of try to train you to focus for long periods of time. So what's a person to do? What do you think is a good way to study or to focus? Long bursts, long periods, short bursts, what do you think? Any opinions? What's a good thing to do? Yes. I'm sorry? Extended periods? Well, actually, the answer is it depends upon what you're trying to achieve, right? So, if you do an analogy with physical training, then there are two sort of diametrically opposing ways of doing physical training. There's endurance training where you sort of go for long periods of time, right? So, what do you call them? You do your, sorry? Yeah, you run your laps or you swim your laps, etc., and you keep going for long periods, right? But then there's speed training. How many of you know about speed training? Yeah, so in speed training, what you do is you run flat out for a ridiculously short distance, right? So if you were doing squash, you might run the length of a squash court, which is not much more than going from, well, maybe 1.5 times that. Maybe you go a round trip on that, but that's sort of ridiculously small. Right? So you run for a ridiculously small distance, but you go all out. You go as fast as you can. And then what do? You stop. And you wait till your heart rate comes back down to normal. You completely relax again. And then you go flat out as fast as you can again. And you just keep doing this over and over again. Right? But each time you go, you're focusing as much as you can. Right? So if you were doing speed training for the mind, what you would think in is, 5-minute periods, 2-minute periods, 1 minute? Right? So you would think for a very short period of time, but you pour all your energy into that minute or two. And then you take a break. It's exhausting. Right? Take a break. What do you do to take a break? Go for a walk, think about something nice, do something else, and then come back and put all your focus in for those 2 minutes. Okay? All right, so back to so let's just spend the last little bit of time talking about functions. Okay? So everyone know what a function is? We've been talking about it a lot, so let's, sorry, can we, so we have only 10, 15 more minutes, so let's focus. Okay, so this is our speed training, it's focusing, okay. Okay, so when we talk about functions, we have a domain and a range, right? So A is the domain of the function, B is the range of the function. The function associates with each element of the domain a unique element of the range, right? So for every x, there's a unique element of the range, which is f of x. Now we'll say that this function is one-to-one if this doesn't happen, right? So we don't want this to happen. So this is not a one-to-one function. If f of 1 is equal to f of 3, that's not one-to-one. That's not good. Okay. So here's an example of a one-to-one function. So if this is our domain, that's our range. We could say f of x equal to x plus 2 mod 15. Right? So 0 goes to 2, 1 goes to 3, 2 goes to 4. Right? 10 goes to 12, etc. Right? That's a one-to-one function. Right? Because there are no collisions. Now we'll say that the function is onto if nothing in the range is missed. If for every element here, there's some element in the domain that hits it. Okay? So, for example, if we had a function where f of, for example, this previous function, it's not onto. It can't be, right? Because the range is larger. So there's no way you could hit everything. So here, we could define an onto function. For example, we could say f of x equal to x mod 10. Right? And now this is going to be an onto function. Because, for example, 0 maps to 0, 10 maps to map mod 11, let's say. Yes? Okay, so f of x is x mod 11. And then 11 gets mapped to 0, 12 gets mapped to 1, etc. And so we have a collision here. So it's not one-to-one, but it is onto. We'll say it's a bijection if it's both one-to-one and onto. Right? So, for example, if we took f of x equal to x plus 3 mod 15, that's a bijection, right? Because you'd have 0 mapping to 3, 1 to 4, 2 to 5, 11 to 14, and then 12 gets mapped to 0, 13 to 1, 14 to 2. Right? So it's just a pairing up. Right? So for every element here, there's exactly one element on the other side. You just pair up the two. That's what a bijection is. Right? Yes?
How's it one-to-one? Like, if you have a 15, wouldn't it map again?
But there's no 15 in A.
Oh, you're saying just the domain doesn't.
That's right. Yeah. So F is it's a map from A to B. Right? So you're given a domain and a range. Sorry. So this A is called the domain of the function, and B is called the range of the function. Yes? Okay? Okay, so here's another possible way that you could compute you could look at a bijection. You could look at 2 times x. So what if you had f of x equal to 2 times x mod 15. Is that a bijection? Yes?
I have a question about range. Because in my head, I always thought of range as the set of numbers that is the natural output of the function.
No,
In this case, we're just like given range.
you're given the range, yes. We are saying f is a map from A to B, and then yeah. So how one uses that function, you could say, is it in the range of f, and is it actually okay? So that's yeah. Okay. So now. What about f of x equal to 2x mod 15? Is it 1 to 1? Should we try it? Okay, so 0 maps to 0, 1 maps to 2 to 3 to 6, 4 to 8, 5 to 10, 6 to 12, 7 to 14. And now let's change colors just to make sure that we can keep track of everything. What does 8 get mapped to? Okay, so 8 goes to 1, 9 goes to 10 goes to 11 goes to 12 goes to, right? 13 goes to 11, and 14 goes to 14 twos are 28, mod 15, 13. Okay, yeah. It's all good. So it's 1 to 1. It's a bijection. How do we know it? Can anyone tell me why it's a bijection? Yes. Yeah, good. It's a bijection because GCD of 2 and 15 equal to 1. What does that tell us? There's a multiplicative inverse mod 15. So what's the multiplicative inverse of 2 mod 15? What's 2 inverse mod 15? Yeah, 8. Good. So you could also define a map from here to here, which is multiplying by 8 mod 15. Right? So you go 0 goes to 0, 1 goes to 8, 2 goes to 8 twos are 16, which is 1. 3 goes to 3 8s are 24, which is 9, and so on. Right? So there's an inverse map. Yes? Okay. How about if you multiply by 3? So f of x equal to 3 times x mod 15. Is that a bijection? Okay, so should we try it? So 0 goes to 0, 1 goes to 3, 2 goes to 6, 3 goes to 9, 4 goes to 12, 5 goes to 0. So we are already not a bijection. 6 goes to 6 threes are 18, which is 7 goes to 8 goes to. Everybody see a pattern? So those are the only numbers we'll keep hitting. It's 0, 3, 6, 9, 12. Yeah? So it's not 1 to 1 onto, not a bijection. Okay. How about if we look at f of x equal to x squared mod 15? Is that a bijection? Surely not, right? So let's try it. 0 goes to 0, 1 goes to 1, 2 goes to, 3 goes to, 4 goes to, okay, it's already not a bijection, right? 5 goes to, 25, which is 10, right? 6 goes to 36, which is 7 goes to 49, which is 9, right? Sorry, 4. Okay, sorry. And what about the rest, 8 through 14? Do we have to figure them out? No, right? Because 8 through 14 are minus of 0 through 7. So when you square them, you'll get the same things all over again. So we'll just hit these same numbers, right? Right, so for example, 8 is minus 7. So 8 squared is the same as 7 squared, which is 4. Right, so you just flip it on itself, and okay, that's what you get. Now, here's one last thing. So how about f of x equal to x cubed mod 15? I'm sorry? What do you think? Is that a bijection? That's actually this is going to be the RSA function. Okay? So let's try it. So 0 goes to 0, 1 goes to 1, 2 goes to, 3 goes to, 3 threes are 3, 27, 12, right? 4 goes to, 5 goes to 5, right? 6 goes to, we are lost, right? Okay, turns out if you fill this in, you get a bijection. Okay? This is really what's behind the RSA crypto system. The fact that when you take x cubed mod 15, you get a bijection. There's a way to generalize this to n being a product of two primes. And that's what RSA is about. Okay, we'll talk about it next time.